Here we're looking at the Ferris wheel problem from chapter 9. The first thing we should identify here is what exactly is a double Ferris wheel. So we've found a picture, a double Ferris wheel, and here I have a better picture than the one in the book given below, has a large rotating arm that's 35 meters. So that's from center to center right here. That's our 30 meters, right? So I'll draw it as if it's horizontally from here to here. That's our 30 meters, which means it has a radius of 15. Attached to each arm is a Ferris wheel that is 20 meters in diameter. So that's here. We have each Ferris wheel is 20 meters in diameter. That's each of these. This blue circle here is 20 meters in diameter, making this radius 10. So here attached to my arm, I have my 20 meter diameter Ferris wheel, or a radius of 10. And I have one of those attached at each side. In addition, it's obviously not just sitting on the ground, so it says it's attached to a 25-meter main support, right? So the double Ferris wheel has a 30-meter rotating arm attached at its center, so that would be this part here, 25 meters off the ground. So right there, we're looking at 25 meters. So now it tells us that this large rotating arm, the one that I have here in the real picture in red, that this keeps spinning around and around and around. And this takes 6 minutes to complete one revolution. So this guy right here, he takes 6 minutes to go all the way around. At the same time, this seems like the best ride ever. At the same time, my blue Ferris wheel keeps spinning around itself. And that one takes 4 minutes to complete one revolution. So this keeps going around and around and around. And it takes 4 minutes for this guy in the big red dot on this wheel to get back to where he started there. All that's happening at the same time, and we're 25 meters above the ground. Now what our real question is to write an equation for your height above the ground, assuming that at time 0, you are right here. So this is you at time 0. So notice at time 0, you're exactly here on that arm. So you're this 25 meters up. So you're starting out at 25 meters up at time 0. Let's scroll down here a little bit. So your height as a function of time is going to be the 25 meters that you're starting at. That's your h of 0, plus however high you are on that big red rotating arm, that big circle. Let's call that f1 of t, plus whatever effects the height has of this blue, the Ferris wheel itself that's spinning around. Let's call that f2 of t. So let's figure out what's going on with each of these functions. So in F1, our red one, so let's use red here, we know that the period is 6 minutes. It takes 6 minutes to go all the way around. So when you use the formula that the period should be 2 pi over b, you get that b is pi thirds. If you're not sure where I got pi thirds, you should pause and calculate that on your own using the formula that the period is 2 pi over b. Similarly, the amplitude of that is going to be the radius of that circle. That should be 15, right? Where the biggest we go from the center is 15 meters, because that big revolution has a radius of 15 meters. At the same time, we're on our little wheel. The little wheel that we've marked in blue has a period of 4 minutes. It takes 4 minutes to go all the way around. So again, using the same formula for period, we find that b, that coefficient, should be pi over 2. Here the amplitude should be 10. The diameter of the blue Ferris wheel is 20. The radius is 10, so the amplitude of that function is going to be 10. It's going to be at a height of 10. Just like the Ferris wheel problems we did in the beginning of this section on trigonometry, these are going to be modeled by a sine function. So putting all of this together, I get that the height of me as a function of time, if I'm starting up at that place where I'm 25 meters off the ground, is going to be 25 plus the height that I am on the big revolution, which would be 15, the radius of the big circle, times the sine of pi thirds t, because that's what I need to get my period of 6 minutes, plus the height that I am on the little Ferris wheel, or the actual Ferris wheel that's going around and around. And that has an amplitude of 10, because the radius is 10, times the sine of pi over 2t, because that was what we calculated the coefficient to be in order to make sure we got our period of 4 minutes. So here is your height function. The second part of the question asks you to find when is the first time that you will be at the maximum height and what that maximum height is. This is periodic. I would encourage you to graph this on your own, either using a graphing calculator or go ahead and log on right now to wolframalpha.com so that you can see a picture of this. And you'll see where it's going to be at its highest. You can probably estimate the highest height, because remember we said that the initial base here was 25, plus when your arm goes around, that arm is 15, the radius. So when you put that all together, you're going to be at a height of about 30, 40, between 40 and 50, right? So we're estimating our maximum height really to be close to 50. We got the 25 from the stand, 15 from the big arm, the radius of 10 from the Ferris wheel you're at. So the maximum height should be close to 50, right? 15, 10. So we're approximating, I'll call this H max. Should be pretty close to 50. So when you're using your graph to read the maximum height, if you're coming up with a number very far off from 50, you're most likely did an error in your graph. But it would make sense that our maximum height is when we're here on the arm. The big, huge circle is all the way up at the top. And similarly, our little Ferris wheel, we're all the way up at the top, right? So that's our 25 again. From here to here, the radius of our big arm revolution is 15. And then from here to here, the radius of the actual Ferris wheel is 10. So now all you have to do is figure out what's the first value of t when you reach that maximum. And I would encourage you to look at a graph of this function to figure that out.